Hi, so before we can get into binomial probability, we do have to talk a bit about counting. And so counting doesn't sound like what you think it might mean, like enumerating digits or something, one, two, three, four. That's not what we mean by counting. Uh, Counting in this case is the theory of answering the question, how many ways are there to something? And so we could see how this relates maybe to probability in that um, when we want to compute the probability of some event E in a discrete probability space, very often the way that that's computed is the total number of possible outcomes. In other words, how many ways are there to something, and then out of which the numerator is the number of ways that E can happen, i.e., how many ways are there for E to happen. And so we want to talk today about two specific types of counting, which are permutations and combinations. So the first thing I'm going to ask ourselves is how many ways how many ways can you arrange three of the letters A, B, C, D, E? All right, and so what we mean by that is we have the letters A, B, C, D, and E, and we're going to pick three of them and and put them in some sort of order, right? So you can start doing this by brute force. So you can say like, oh, A, B, and C, A, B, and D, A, B, and E, A, B, B, A, C, B, C, A. But if we do it like that, then clearly this is going to take you a long time, and uh, it'll be really annoying. And when you're done, when you can't think of any more combinations, you can never really be sure if that's because you got them all or because you just can't think of any more. So what we're looking for is some systematic way of being able to count these arrangements, maybe without having to do them and knowing that our answer is going to be right. So the first thing I'm going to do is say, all right, maybe instead of uh, three of the letters, we can sort of ask ourselves a kind of degenerate uh, a version of this question and just ask ourselves, well, how many ways are there to do this with just one letter? Um, and well, it's kind of obvious that with just one letter, there's five ways to do it. I could say A, B, C, D, E, right? Those are the number of ways that I could take two letters, or sorry, one letter out of my five and arrange it. And so there's not really any arranging to do if you only have one letter, but uh, so, so we are. Now, let's go from one letter to two letters. Well, once we have two letters, we should note that, all right, every arrangement has to start with some letter. And already over here, you can see that I already have all the ways that, in a sense, that my arrangements could start, right? All my arrangements of two letters either start with an A or B or C or D or an E, right? And so let's think about how many ways an arrangement could start with A. Well, you have AB, AC, AD, and AE, right? you basically have uh, four choices, right, for your second letter, given that A is your first letter and you've already used A, so we have to pick some other letter for the second choice. And so we would note that that the arrangement that starts with B would behave similarly, right? We'd have, uh, sorry, BA, BC, BD, and BE, right? And so there's also four choices here, right? And there's not enough space or time to go through them all, but do we all see then that each one of these uh, letters here branch off to four choices in the second row here? So uh, at the end of all of this, there's going to be 20 ways to arrange two letters of these five ways to arrange one letter, 20 ways to arrange two letters. And this 20 then is, sorry, let me switch back to blue. This 20 is 5 times 4. All right. So now we can go to 3 letters. So let's pick one of these branches here, AE. How many 3-letter arrangements are there that start with AE, say? Well, there's AEB, AEC, and AED, right? That's it. And we could see how we get those 3 choices. We say, all right, we've already used an A, we've already used an E. So the choices left are B, C, and D. There's 3 of them, right? And so we have 3 choices for this AE. And we would have 3 choices for every single one of these. Draw a bunch of lines here as well. So if I total all of these together, the number of ways that I should be able to do this is 5 times 4 times 3, or 60 different ways to do that, right? And you can see how this would continue if we had to go on to say 4 letters, right? If we had to say 4 letters hypothetically, then every one of these choices, there's only 2 choices each now, right? AEB, say C, and AEBD. And so if we had 4, then we'd have 5 times 4 times 3 times 2, or 120 choices, right? And then in the very, very last stage of this, I'm running out of room here. So let me just maybe go over to another slide. Let's pick one of these, AEBD maybe. If I pick AEBD, how many different ways are there to make a 5-letter arrangement that start with AEBD? Well, there's only one choice left, right? AEBD, C. So there will also be 120 choices here. All right? And so to recap, if we have 5 letters, or let's say 5 objects total, the number of ways if I select let's say we select some number of them to arrange and then number of arrangements. Um, let's switch to this color maybe. All right, if I select one object, there's 5 ways to do that, right? If I select 2 objects, there's 5 times 4 ways to do that, which is 20. If I select 3 objects, there are 5 times 4 times 3, which is 60 ways to do that. If I select 4 objects, it's 5 times 4 times 3 times 2 equals 120. And if I select 5 objects, it's 5 times 4 times 3 times 2 times 1, which is also 120, right? Because by the time you selected 4 out of the 5 objects, there's only one choice left at the end for the 5th. What about 6 objects? Well, you can keep playing this pattern out if you want. You could say 5 times 4 times 3 times 2 times 1 times 0, which is 0. But it's kind of obviously 0, isn't it? Right? Like if I have 5 objects, how am I going to pick 6 of them? That just doesn't make any sense. So 0 is clearly the right answer here. All right. And so if we follow this same logic, we should be able to see that let's say a k permutation of n objects is a selection and arrangement of k of the n objects. All right? And the number of ways to do this is denoted in Desmos. We would use the permutation function here, npr nk. It is computed exactly the same way. So recall that in our initial example, n was 5 and k was 3. And so what we would expect is some generalization from that. So n times n minus 1 times dot dot dot. And we're looking at k objects total. So the last value here is n minus k plus 1. Right? And so this whole product here can be simplified to be n factorial over n minus k factorial. All right. I suppose I should talk about what the factorial means. N factorial is simply the product n times n minus 1 times dot 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 to 1 if n is bigger than 0, and it's just 0 factorial is just defined to be 1. Now, there are a number of reasons why we would define 0 factorial to be 1. This is a natural question that comes up, like why isn't 0 factorial 0? And the basic answer to this is n factorial measures the number of ways I take all n objects and arrange them. And so if I have no objects, how many ways are there to arrange them? Well, there's really only one way, and that's I don't arrange them. More technically, an arrangement of objects is a bijective function from a n element set to itself. So if I have the empty set, that bijective function is just the identity morphism on the empty set. But that's a really technical definition. But I just wanted to show how we can compute this in Desmos if we wanted to. So if we go NPR, all right, 5, 3 is 60, like we had originally talked about when we did this by hand. And we should note that I could NPR 5, 2, say, gave us 20, like we had said it would be. If I put in 1 there, it was 5, like we said it would be. If I put in 4, it should be 120, like we said. And if I put in 5, it's also 120, like we said. But I should also note that we had this formula for n and r. So if I said n was 5 and r was 3, then that gives us 60, like we said. 1 gives us 5, 2 gives us 4, or sorry, 2 gives us 20, 3 gives us 60, 4 gives us 120, 5 also gives us 120, right? It's the same things. And so using this, you can very, very quickly compute these permutations as needed. All right, so moving on to the next part of this discussion here is combinations. So, how many ways can I select k out of n objects? And so what's the difference between this and what we had just been talking about? Well, here we have permutations, and that's the number of ways to, or a permutation is a selection and arrangement, right? So if I pick k out of the n objects and I arrange them. So if we go back further to these, right, AB and BA are considered different arrangements, but they're the same selection, right? Like it's still the same 2 things I picked out of the 5. And so very often, the order in which I pick things does not matter, right? And so let's say there's a I don't know, a plate with 10 cookies on it. I'm going to pick 3 of them to eat. The order in which I pick the cookies to eat isn't really going to matter. They're all going to get eaten, right? On the other hand, if you had like a class of 20 people and you're going to pick or maybe a club with 20 people in it, and you were going to pick someone to be president, vice president, secretary, treasurer, who gets assigned to what makes the difference, right? I can select the same four club members, but give them different roles. And this is different than if I just selected four club members to be on a committee, then it doesn't matter who I picked first, it's just the four with equal standing on the committee. So uh, here I want to select K of the N objects without order. And so to illustrate how I would do this, I'm going to concretize this by saying, uh, by sticking with the numbers we used before, 5 and 3. Now, I'm going to go ahead and say that's one of the possible ways that I could select uh, 3 out of 5 objects. And let's assume that A, B, C, D, and E are store of 5 objects. What I'm going to do now is I'm going to use the fact that I know how to collect or count objects with arrangements to figure out a way to count objects or selections without arrangement. So ABC, let's say, is a selection of objects with arrangement, A and then B and then C. So the question is, how many arrangements are there that use the same selection, A, B, and C? It's like, well, we can start writing them out. Where there's ABC and ACB, there's BAC and BCA, C8, B and CBA. And we can look at that and say, all right, is that all of them? Yeah, it should be all of them. How do I know that's all of them? Well, besides the fact that I can't really see anymore, that's 6, right? There are 6 items in this column. And that is the number of ways I can arrange 3 objects. This is 3 factorial, right? And so let me pick another selection. Let's say A, B, D. So that's a different selection as well, and an arrangement that goes with it. But how many things will be in this column here? And it's like, well, there's a ADB, BAD, BDA, DAB, DBA, the same 6, right? Because it's still 3 elements, and that's, or 3 objects, and that means still 3 factorial or 6 total arrangements. And so how many columns will I end up with? Well, what I know is that there's 60 hold on, I'm going to give myself a little bit more room here. What I know is that there's 60, or 5 factorial over 2 factorial total arrangements, right? And every one of these columns has 6 items in it. And that must mean I must have a total of 10 columns. That 10 columns comes from the 60 divided by the 3 factorial, which is in fact 5 factorial over 2 factorial 3 factorial. And so if instead I go back to n and k, what I should get as a final result then is n factorial, the 2 is n minus k factorial, and the 3 is to k. Right? So a combination is a selection of k objects out of n and the number of combinations is that, so the number of nk combinations is denoted n choose k. So by the way, this is not the same thing as n over k. And n choose k is computed n factorial over k factorial n minus k factorial. And in Desmos, this is denoted NCR NK. All right. And to again, to illustrate how you could do this in Desmos, if instead of NPR I had NCR, here, and instead of n minus r factorial, I had r factorial. And you know what? Instead of, I'm just going to put n and r here. When n is 5 and r is 3, we get 10, which is what we said when we did this computation, right? When n, let's say if n is 5 and r is 2, we also get 10. Now this is a little curious, right? Because when we did permutations, those numbers would have been different. Here, they're the same. And so why would that be the same? Well, one way to think about it is algebraically. When r was 3, this is 3 factorial, this is 2 factorial, right? When r is 2, this is 2 factorial, this is 5 minus 2 or 3 factorial. So the denominators of these fractions are the same. The numerator is always the same. So the fractions themselves are the same. But that's really kind of the not interesting way to think about it. Another way to think about it is, all right, if I have 5 objects, A, B, C, D, and E, whenever I pick 3 objects, I'm also picking 2 objects at the same time. So if there's 5 cookies, say I'm going to eat 3 of them, that's the same thing as leaving 2 of them on the plate. All right? And so whenever I make a selection of k or r objects, I'm also making a selection of n minus k or n minus r objects. So if n is 5 and let's say r is 1, all right, there are 5 ways to do that. That makes sense, right? If there's 5 objects, right, and I have to pick one, there's 5 ways to do that. And n choose 4 is also 5. And that's for the same reason. If I have to pick 4 of these objects, there's 5 ways I could leave one behind. And so that's still 5. N choose 0. Again, if I have 5 objects and I'm not going to pick any of them, then I'm not going to pick any of them, right? And there's only one way to do that. 5 choose 5. Well, if I have 5 objects, I'm going to pick all 5 of them. Then there's only one way to do that. I pick all 5 of them. All right. And so that gets us to one of our identities, and it's the only one I'm going to talk about. There's many such identities. About the counting coefficients, but we won't get into them here. The number of ways to pick r out of n objects is the same as picking n minus r out of n objects. All right, and so this gives us the background that we'll need going forward to talk about binomial probability.